Right, thank you very much. I'm going to present results from a rather small study that we did together with the company Fountain Ventures, as well in cooperation with the Swiss Material Science and Technology Institute. What we were looking specifically at is indoor air quality issues, and specifically focusing on particle behavior in rooms where electronic and conventional cigarettes are being smoked. So the rationale for the study was that I see that there are reports flowing already, and I think that we just wanted also to piggyback to these reports about what happens to the specifically exhaled portion of e-cigarette that contributes to the presumably worsening air quality in rooms. And we looked at the particles, not specifically gases, but particles. You can see that particles here are in parentheses. I would like to take 1 minute to explain the complexity of this issue, because not all of you are aerosol scientists as myself. And aerosol science is a very broad area. It has societies of its own, it has conferences on its own. And the complexity of particles to gas systems is so large that it's very much important to understand what we measure, how we measure, and when we measure, and all of these aspects. And interestingly, that a lot of regulation that comes right now, it focuses on a specific property of particles which is associated to mass of particles. But particles may be anything that we can measure at any time that is suspended. So it does not specifically refer to solid particles or liquid particles. And let's say if these are liquid particles and they are measured with a mass method, we cannot probably get any of mass of liquid particles, because they will evaporate during conditioning of filters, let's say, where they are collected. So measures as PM2.5, PM10 are rather not so suitable, I would feel, but I don't have any data to piggyback that. But we did have some advanced instrumentation employed to show the behavior of particles that are being exhaled during the smoking of e-cigarettes. What we did, we employed a chamber, which is a room within a room, and it had forced ventilation, which is supplied by air handling units, so that we can control air change rate. And then the air has been filtered additionally by activated charcoal to remove any possible compounds that may come from outdoors, as well as filtered by HEPA filter to remove additional particles, and then distributed in the room. Then you can see a chair where the smoker is sat, and in the lower right corner you can see the actual picture. And that chair was being moved in a distances, let's say 0.5 meters, 1 meter, and 2 meters from the bystander, or by-sitter, I would say. So there you can see a funny robot, which is actually a mannequin. It represented a seated person, and it has been heated so that the surface temperature of a mannequin was comparable to that of a human person. And so that the smoke was approaching the bystander, and it has been measured by rather advanced aerosol devices, which included fast mobility particle sizer, electric low pressure impactor, as well as scanning mobility particle sizer. These devices are capable in measuring not just PM2.5 and PM10, but the entire range of particle sizes, starting from, let's say, 10 nanometers and going up to, let's say, 10 micrometers. So that's several orders of magnitude of particles. And then we also controlled for ventilation rate. We try to see if there is impact of ventilation rate in the room, and the distance effects, and the smoking effect as well. These are the results what we obtained. Let's say if a smoker sits at 0.5 meter to the bystander and smokes directly to the bystander. So of course we see as inhaled, I mean the smoking, meaning that the exhaled smoke is being puffed directly to the face of bystander. We see the increases in concentration in a matter that are displayed. First graph displays e-cigarette, another graph displays conventional cigarette. The patterns are rather similar. There is a difference in concentration. So you see that the concentration of particles is 10 to the 6 in case of e-cigarettes, and it goes up to 10 to the 8 in case of conventional cigarettes. These are number of particles. We counted not the mass, but each particle. And so there is not so much difference, but then there is after puffing period where the puffing is over, and we keep the chamber for half an hour just at the same ventilation rate. We can see that with the e-cigarette, the concentration falls to the background at the level 10 to the 4. Right now we also have probably 10 to the 4 particles in per cubic centimeter. You can imagine 1 cubic centimeter has 10,000 and particles. So that's a normal level in occupied rooms. With conventional cigarettes, we saw a bit different behavior. You can see that after the puffing is over, the concentration falls, but it starts increasing. And of course, the increase is not so severe as in puffing, but there is an increase and then the slow decrease. So that was a phenomenon that we wanted to understand more. So that was 0.5 half of a meter from bystander. If a smoker moves further away, you can see that the puffs are not so evident because the puff has time to disperse in a room. And they are not so evident, but there are some indications that there is some active process happening, especially in conventional cigarette. One puff was able to travel directly to the bystander. But again, after period is rather similar. With e-cigarettes it's rather stable, and with conventional cigarettes we see again an increase of particles and then the decrease. So we examined these peaks separately, and for example, comparing products, we don't see much of a difference in each puff. You can see that there is an increase and decrease, let's say 5-second process or 10-second process, depending on the distance that the potential exposure may happen. But then if you see the effect of a distance in the lower graphs, you can see that of course the closer we are to the smoker, the higher exposure we can get. And you can see the 10 to the 6 level, and then if you move to 1 meter, it's lower, and then in 2 meters, the puff is almost dispersed. So that stands pretty much to both types of cigarettes. But then if we look at the particle sizes, what are generated, this is in the x-axis, you can see the size of a particle. Ventilation was kept at 2 air changes per hour. The distance, let's say first graph is 0.5 meters, another graph is 2 meters. We can see that the sizes of particles are different a little bit. E-cigarettes produce smaller particles at around 100 nanometer mode. Conventional cigarettes produce particles at around 200, 150, 200 nanometer mode. Interestingly, when we sampled at 2 meters distance, the particles of e-cigarette become smaller. That means that while they travel through the room, they shrink. And that was a phenomenon that actually we did expect, considering the composition of these particles. But it was very interesting to get the quantitative expression. While in conventional cigarettes, the particles don't shrink and they remain what they are. And then in the lower graph, you can see that, let's say this is the graph for e-cigarette, different distances. At 2 meters, while they travel, they shrink to, let's say, 40 nanometers to 50 nanometers instead of 100 to 200 nanometers. Why these particles shrink? And it has to deal with composition of these particles. You probably know that the relative composition, most of the exhaled aerosol of e-cigarette is water vapor. This is for composition of exhaled composition of e-cigarette. And that vapor and polypropylene glycol and glycerin are also volatile compounds. So while they travel in the room, they evaporate. And the main message here is that pretty much they don't accumulate in the room. If you remember those graphs that I showed, that in conventional cigarettes, the puff is out and then it spreads out, and then the more puffs you take, the concentration becomes higher in the room, in the entire room, because ventilation is not capable to remove the particles. It's much slower process than the smoking itself. While in case of electronic cigarettes, they evaporate and almost no particles are left in the room. And they are converted to vapors. So with the vapors, in case of water is fine. Then, of course, it comes down to breaking down these vapors, which I saw quite a few studies, what's in those vapors. And right now, the previous presentation also compared to the threshold values. Some of those are reported by Fontaine Venture in a paper that you can see. But we did not specifically look to the very detailed composition of the vapors. It was just to test hypotheses about the particle behavior, so-called particle. But generally, the conclusions are that the variation during the puffing is very rapid and is associated with direct impact of puffs. And once we puff, the concentration increases several orders of magnitude, but drops down in 10 seconds during electronic cigarette usage. But in conventional cigarettes, the puffs are also rapid, but the concentration particles accumulate in the room and before they settle or are being removed by ventilation, which are much slower processes. So that was caused by the shrinkage of the particles, let's say, and the higher the distance, the less chance that we will get any of those particles inhaled. And the main cause of that is, of course, that the main constituent is water, which is being exhaled. While in case of real cigarette, these are combustion particles. All right. Thank you very much.
Thank you.